All right, guys. Today we're going to be solving dynamics problem 3.174. The problem reads, an artificial satellite moving in an elliptical orbit has a velocity of 2,500 kilometers per hour at an altitude of 2,200 kilometers at point A. Determine its velocity at point B, where the altitude is 2,500 kilometers. Treat the Earth as a sphere of radius 6,371 kilometers and use g acceleration due to gravity 9.825 meters per second squared at the Earth's surface. All right, so in order to solve this problem, we're going to use conservation energy. The equation for conservation energy has the initial on the left and the final energy of the system on the right. So in an equation form, they look like this. Initial potential energy plus the initial kinetic energy is going to be equal to the final potential energy of the system plus the final kinetic energy of the system. We know potential energy is equivalent to mass times g times h for height, initial, plus for the kinetic energy, we can expand that into 1/2 mv squared, so the initial velocity squared here. And that's equal to the same equation just for the final on the right side. So mass times gravity times final height of the system plus 1/2 mass times final velocity of the system squared. Now we have mass common to all terms, so we can divide each term by the mass, by m, and that will cancel everywhere here. And now we have our equation all filled out. We now just need to simply substitute in the values and the numbers in we have and solve for our final velocity df squared here. So we know our g is going to be 9.825 meters per second squared. We multiply that by the initial height of the system, which is 2,200 kilometers. Now, one thing to pay attention to that's important is that our height here is in kilometers, but our g value is in meters. So we need to make these common terms, same terms. So you need to multiply by 1,000 meters and divide by 1 kilometer. This conversion factor will get us our units in meters squared over second squared. Kilometer per kilometer here will cancel out, as we see here. Okay? Plus our second term, 1/2 initial velocity of the system squared, of the satellite. So we have 1/2, and we have our initial velocity is in units of kilometers per hour. We have 25,000 kilometers per hour. So we need to also go ahead and convert this into meters per second. In order to convert the top part into kilometers, we multiply by 1,000 meters and divide by 1 kilometer is a kilometer. We're also going to divide by 3,600 seconds and divide that by 1 hour. So this will get us now to meters per second. As you can see, kilometers per kilometer cancels. When we divide by hours in the bottom of this fraction, hours will flip to the top, take the reciprocal, and hours per hours will also cancel. So we have meters per second multiplied by this conversion factor. Okay? And so then we got also remember to square this. This is the initial velocity term here, bi squared. This is now going to be equal to the right side of our equation, this term. So we have g again, which is 9.825 meters per second squared. That's multiplied by our initial height, final height of the system, which is 2,500 kilometers. We're going to convert that into meters as well, so multiply by 1,000 meters, divide by 1 kilometer. As we can see, kilometer per kilometer will cancel. We have meters here, so that's good. And then we have to include our last term, our 1/2 final velocity squared, 1/2 VF squared. Now make sure we can see this all. 1/2 V final squared. Okay, and from here, it's simply a matter of substituting these numbers into the calculator and solving for those values. So we have 9.825 times 2,200 times 1,000, and we have 21,615,000. So we have that here, 21,615,000 meters squared per second squared. Plus, we're now going to multiply the second term, and for that we have 25,000 times 1,000 divided by 3,600, which we have this here. We then square that and then multiply it by 1/2. So divide by 2, and we get 24,112,000 and so on. So plus 24,112,654.32 meters squared per second squared, equal to, on the right side, we now have our G value, 9.825 times 2,500 times 1,000, which gives us 24,562,000 and so on. So 24,562,500 meters squared per second squared. Plus, again, our 1/2 VF squared term, 1/2 final velocity of the system squared. Okay. So now we're going to combine these terms. So we go ahead and add up our two terms on the left. We have 21,615,000 plus 24,112,654.32. Okay. Then we're going to subtract the term on the right minus the 24,562,500 term. Okay. We're then going to multiply that by 2 because the 1/2 here, we can't further multiply it by 2 here. Okay, so times 2, and we get a value for VF still squared, VF squared of 42,333,08.64 meters squared per second squared. Okay. Okay. Our last step now, we're going to go ahead and square root our VF squared term to get just VF. So the final velocity will be the square root of this number we've calculated so far. So we take the square root, and we get 6,506.17. Square root of meters squared is meters. Square root of second squared is just seconds, so meters per second. We can then convert that into kilometers per hour if we want to compare it to our initial speeds we were given. So times 1 kilometer over 1,000 meters. And also go ahead and convert that into per hour. So times 3,600 seconds divided by 1 hour. When we do that, we get a final velocity. If we can see. Okay. We get a final velocity of 23,422.2 kilometers per hour, which makes sense. Our velocity is less than it was at point A. We gained altitude, so our energy has to be converted from kinetic into potential. By doing that, our speed will go down, our speed will decrease. So this makes sense for our final velocities we have here. Be sure to like and subscribe. Thanks, sir. I appreciate it.